Welcome back. Ready for some more rules? Well, we actually aren't going to talk about rules in this video. We're going to spend some time applying them, and we'll have to use some of them, and we're going to apply them to some geological examples. And one of the first examples, we've already talked about this porosity-depth relationship. It's an exponential decay function. We'll talk about that. We'll talk about the energy earthquake magnitude relationship, and we'll talk also about a mathematical relationship which describes the thickness variations through time in an extensional basin. So for the porosity gradient, if we want to calculate the porosity gradient, that's a fairly straightforward effort. We just talked about the rule for exponential differentiation. We have a couple constants in here. Phi 0 is the porosity at a depth z equals 0. So when z is equal to 0, we have e to the 0, which is just equal to 1. So phi is equal to phi 0. The factor lambda, that represents the depth at which the porosity drops to phi 0 over e. So when z is equal to lambda, this is equal to minus 1. So we have e to the minus 1. 1 over e is equal to 0.368. And so we have phi equal to 0.368 of phi 0. The derivative, remember, it's just a two-step function, or it's two-step process. We incorporate the chain rule. We start by rewriting the original function, phi 0 e to the minus z over lambda, and then we multiply that by the derivative of the terms in the exponent. And in this case, the exponent is fairly simple. We have minus z over lambda. The derivative of that is basically just minus z over lambda. So we have, or minus 1 over lambda. So we have 1 over lambda times phi 0 e to the minus z over lambda. That gives us a minus phi 0 over lambda e to the minus z over lambda. So a fairly straightforward relationship. Notice up here we have the base e, so that makes the application of this differentiation rule fairly straightforward. When we have something like, this is a relationship between earthquake energy and the magnitude of an earthquake, and you can see it's an exponential growth function. The energy release increases as magnitude increases. But we have a complication here because we don't have base E. We have base 10. And so remember, what we needed to do there was convert the base 10 in this case to base E. And again, this is just a relationship between the energy released by an earthquake of magnitude M. So when we have exponential function which has an arbitrary base, such as 10 in this case, then everything else is the same. We rewrite the function. You can see the parts of the original function there, 10 to the 1.5 m. You can see our a there. We multiply that by the derivative of the exponent. There's our 1.5. The additional term in here, the natural log of 10, is the term that we have to add when we're dealing with functions, exponential functions, where the base is different from the natural base e. So that there's just a couple quick examples. Here's another example. This is an example that you'll find in Waltham's text, Mathematics, a Simple Tool for Geologists. This, I'd recommend this. This is a good text. Has a lot of good geological applications, and would actually make a good supplement for a lot of the things that we're discussing in the GeoMath video sequence. Here we have a relationship between the thickness of the sediments deposited in an extensional basin through time t, eventually reaching some maximum thickness as t goes to infinity. The basin will fill up and it will have a thickness of, will have sediments that thicken to S max. So we're interested in what is the sedimentation rate. This would be where we'd be applying our differentiation rules. We have ds dt. What is ds dt in this case? So in order to take this derivative, well, you know, you might start by simplifying this term in brackets. We could just distribute the S max through these two terms, so we'd have S max minus e to the minus t over tau. Think about what tau represents in this instance. In the next video, we'll spend a little bit of additional time on this, but consider that tau in this representation, since we're subtracting e to the minus t over tau from 1, will represent the time it takes to fill 63% of the basin. So again, start by distributing S max and the derivative operator so that we're differentiating S max with respect to t. This is a constant, so we know that's going to go to 0. This is a constant, so we pull it outside the derivative. We don't have to apply the product rule. We're just differentiating e to the minus t over tau. So we've got these two terms here. And we know that we just rewrite the original function and then multiply it by the derivative of the exponent, which in this case is, what's it going to be? The derivative of minus t over tau with respect to t is just going to be minus 1 over tau. So we have a minus 1 over tau times a minus S max. The minus signs cancel out. We end up with the sedimentation rate being equal to S max over tau e to the minus t over tau. Okay, so sediment thickness variations through time, we're subtracting e to the minus t over tau from a constant. In this case, in this graphical representation, our S max is 1, let's say. That makes it simple. So here's e to the minus t over tau, down through here. This is 1 minus e to the minus t over tau. So this gives you kind of a visualization of what we're doing. We're just kind of subtracting that. Now what I'd ask you to think about is the relationship of tau. You know, again, we'll cover this kind of briefly, but remember for e to the minus t over tau, this is the, well, where did I, okay, there we go. Sorry about that. This is the, when e to the minus t over tau is approximately 0.37, when t is equal to tau. So in this particular case, e to the minus t over tau drops to 0.37 of its maximum value. Okay. Now, 1 minus e to the minus t over tau, rather than drop through time, it's going to rise asymptotically through time and converge on S max, which in this case is just 1. So this line, if we go to infinity in time here, will eventually be equal to 1. So when we're dealing with the function 1 minus e to the minus t over tau. Tau represents the time it takes for the basin to fill up to 0.63 of S max, whatever S max happens to be. In this case it's just 1, but this is 0.63. So, since our maximum is 1. Okay, so those are a few geological examples that give you a sense for how you can use some of your differentiation rules. The next time we're going to take a look at graphical relationships and kind of work backwards. Let's say you have these functions here, which are 1 minus S max in this case, we can tell is 3. So S max times 1 minus e to the minus t over tau. We have two different curves here. What can we tell from looking at these two curves? So talk to you next time.